Hello, I'm Audrey Kavam, and I'm a physicist with the University of Massachusetts Amherst. And I'm based full-time here at CERN, working on the ATLAS experiment, which is about 100 meters below me.
The ATLAS experiment is designed to detect the products of proton-proton collisions at CERN, which is the laboratory at the Large Hadron Collider. And so this collider allows us to recreate the early moments after the Big Bang and study new fundamental interactions and search for new particles. ATLAS is the largest collider experiment ever built to date. It's the effort of about 6,000 people. We have a really large collaboration, people coming from all over the world. I think at the last count we had about 270 institutes from 40 different countries that are contributing to building, operating the experiment and analyzing the data. I have been chosen to lead the ATLAS experiment for the next 2 years, and the name spokesperson is a misnomer because this is not what you might expect from that name. It's really more executive director or something like this. It's the person really leading the execution of the physics program for the experiment, the future running, the data collection at CERN, interacting with the CERN directorate, interacting with the funding agencies, interacting with all of the collaboration members to chart a course for the next 2 years and beyond. Our main goal is to really understand the universe at the most fundamental level. And this is really an effort that's been going on roughly for the last 100 years. The Higgs boson was discovered about 10 years ago, and we still do not understand its properties very well. It's a very different type of new particle that is responsible for giving other particles their mass. And this is a completely new type of interactions, unlike anything we have discovered before, like electric force or magnetic force or gravitational force. So there's a new type of interaction which is mediated by the Higgs boson. And the Higgs boson may very well be a portal, for example, to a dark sector. For example, to particles of dark matter. We have detected a wide open door into new phenomena.
So these boards take raw detector information and then quickly reconstruct particle trajectories. And this helps us decide if the event is interesting enough that we want to save it for further analysis downstream, so it passes our trigger, or it doesn't pass our trigger and then we discard the event and just move on to the next one. So this is a very critical part of our data taking process.
We are in the middle of run 3. We are collecting larger amounts of data than ever before. Recently, actually, we passed the 1 exabyte amount of data managed by the experiment. This is about 20 million phones. If you want to store all of these data onto a typical phone, it would require an enormous number. Our group here at UMass is involved in analyzing the data, but also processing these data. So we are managing a so-called Tier 2 computer center in Holyoke that is part of a very large worldwide, what we call the worldwide grid, which consists of hundreds of sites worldwide that receive the data, process the data, make it available for data analysis by our graduate students, our postdoctoral associates. We are developing new methods based on novel ways to use neural networks to extract most of the information out of the available data.
I work on the New Small Wheel project, which has been one of the major upgrades for Run 3. So you can see the New Small Wheel detectors are these kind of bronzy disc-shaped detectors here. They're part of the ATLAS muon spectrometer, and they're designed to operate in very high luminosity conditions.
More than 100 years ago, when the electron was discovered, it was utterly useless. Quantum mechanics was believed to be utterly useless, a purely almost philosophical development. And now all of the devices that we use, phones, LEDs, completely rely on the understanding of fundamental particles at the subatomic level based on quantum science. So this fundamental understanding of particles and their interactions may not seem directly useful, but 20 years, 50 years, 100 years from now, they may turn into the next big thing.